Hello again. Thanks for joining us. This is Space Nuts. My name is Andrew Dunkley. Yes, it is. I just checked the name on my shirt. So, good to have your company on another edition of Space Nuts, episode 380. And you know what that means? It's the one after 379. It also means that we are doing 100% audience questions, and we might even answer one. And we're going to be looking at things like black holes. But there's other stuff. We've got a question about different fields in science. So that'll be a fun discussion. The LF bot has come up as a question. Also questions about time. And I really like the sound of this one, unborn universes. We'll be discussing all of that very, very soon. In fact, right now on Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me to cover all of that and much, much more is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you this fine-ish day?
Yeah, avoiding storms. It's been pretty wild and woolly around here. And I noticed on the radar this morning it's been pretty wild and woolly all around the coast too.
So I drove up from Canberra to Sydney yesterday afternoon.
Oh, that would have been fun.
And went through the heaviest rain I've ever seen on a drive.
Wow.
I've never seen anything like that. I could probably see about 3 meters in front of the car. It was unbelievable. And most cars were pulled off the road with their hazard lights flashing. Dozens and dozens of cars off the road.
I got caught in a hailstorm coming home from Singleton to Maitland on the New England Highway many, many years ago. And I had to pull over. I couldn't see a foot in front of the car. Yeah. But then when I hit Maitland, I thought, oh, my gosh, that had cyclonic conditions and it was an absolute mess.
Yeah,
That and you know what? Those storms are getting much more common now, which is unfortunate.
I wonder why.
I think the funniest story I've heard so far, because there's always a funny story when it comes to natural disasters, is there's a monument to a whale or something in one of the south coast towns, and it fell off its foundation and floated down the street.
There you go. That would be nice. I like that. Yeah,
it's pretty good.
Yeah, it was anyway. Certainly yesterday, I'm glad that I wasn't staying in that area because I think they've had serious flooding.
Yeah, they have.
It was on the news this morning. So yes, we are all experiencing the consequences of climate change.
Looks that way in the new whatever it's called, epoch that we've entered. I can't remember. Let's get some questions. Sorted out.
I can't remember it either.
Yeah, I can't either. I'll look it up.
Ends in C-E-N-E, I know that.
Yeah, the Apophocene.
Yes, I think that's it.
Sounds right. Close. All right, we've got a question from Bill, and guess what the topic is?
Hi, guys. This is Bill Bogan from Ann Arbor, Michigan. And I have a question about black holes, of course. Like, do they actually have to be black? I was playing with the equation for escape velocity, square root of 2gm over r, and said, okay, well, what if you set that to c, and instead of mass, you use density, and it all comes out to be r times the square root of density equals 1.269 times 10 to the 13. Okay, so I thought, well, what's the density of a neutron star? Oh, that's like 3.7 times 10 to the 17 to 5.9 times 10 to the 17. You plug that in, and you get a radius of 16.5 kilometers. So, in other words, if you had a neutron star with a radius of 16.5 kilometers, it would be a black hole, but would not be a singularity. Does this make any sense? And, of course, if you had something like a quark star, which is being theoretically considered, then you get a density of 10 to the 20th and a radius of 1.3 kilometers, which I have no idea if that's even theoretically what a quark star could be. So, just wondering, can you have effectively a black hole that is not a singularity? Thanks.
Okay. Thank you, Bill. What do you think, Fred?
No, I think the answer is yes. You can, because look, I'm not a black hole specialist, as you know, but certainly thinking about some of the reports I've read from colleagues who are black hole specialists, that yes, you could have a singularity you could have a black hole which does not have infinite density, so it isn't a singularity, but it still has a high enough density that you have an event horizon and the point of no return for light waves. Neutron stars do have some of the properties of black holes in that their density is so high that they are certainly curving the space around them. And so you're going to get some peculiar optical phenomena because it's acting like a gravitational lens. Quark stars, likewise, if they exist, we don't know whether they exist or not. But once again, you would have space-time curvature associated with that. So I think, I think Bill's right, though. I think you can have black holes that aren't singularities.
Wow. But we haven't seen anything as such.
I mean, well, we don't know. That's the problem, because you can't probe beyond the event horizon. All you can see is something that's got very high density. Now, the formal definition of a black hole is a point with infinite density. And, if you've got something that's very, very dense indeed...
like me.
Well, yes, I can see the space-time curving around your head there. No, that's right. It's how do you tell the difference between something that is very, very dense but not infinite and something that is infinite? One's a singularity, one isn't. But yet they both generate an event horizon and have the same properties. Effectively, you've probably got an accretion disk and all the rest of it. So, yeah, interesting stuff, which if I knew more about black holes, I'd probably be able to answer more cogently.
I think we were all wanting to know more about black holes, otherwise we wouldn't get so many questions on them. What I struggle with is how can you have something infinite in a world or a universe that has limitations?
Yes, that's right. That's why it's a singularity, because it doesn't fit the normal, prescription for the world and the universe. Normal space-time. Space-time is sort of twisted up. It's basically infinite density. Yep. Yeah.
All right. Thank you, Bill. Hopefully that helped, and well done on the mathematics. Yeah.
Yep.
I'm so jealous. We've got a question from Rennie. Rennie often sends us audio questions, but he's sent us a text this time, which I've got to find because it's not where I thought it was. Here it is. It fascinates me that there are so many specialty fields in physics and astronomy. Can you briefly go over fields of specialty research and study for physics and astronomy? As, for examples, there might be scientists who only study the sun and its behaviour. Thank you for all the information packed into each episode with a touch of humour. We need this desperately. Thanks again, Rennie Traub. Thank you, Rennie. Lovely to hear from you, usually as an audio question, but you sent us an email for a change, which was nice. Yeah, lots of fields of science, I imagine, with specialties, Fred?
Absolutely. And it is absolutely true that astronomers do specialise. What tends to happen is that they do a degree in physics or astronomy. They'll be in a university that has a speciality whose teaching staff, who are also researchers, actually they all concentrate on one particular area, and those particular areas are pretty well defined, but they also are a bit blurry now because we are seeing a lot of interchange between them. And what I was going to say was then typically what happens is that the person if they stay in that university, they do a doctorate in whatever topic it is that department specialises in, and they spend the rest of their career doing that. Now, I think that is less true now. People do tend to bounce around a bit more now than they did. But just to kind of, go through some of the things. Yes, some astronomers do study just the sun. We usually call them solar physicists. The sun's environment we usually call space physics, and because that's the area. It's we often talk about space weather, which is the physical properties of the interplanetary medium and the Earth's location within that. And then you you get to stellar physics is the evolution of stars, the mechanism and processes that lead to the origin of stars, their evolution throughout their lifetimes, star death. Often people concentrate on the end products of stars, whether they're supernovae or neutron stars. All of the things that we talk a lot about are the end products of stellar evolution. That's a speciality in its own right. And then you've got people who look further beyond and study the galaxy, our galaxy, the structure and history of our galaxy. And that's an area that I've been involved with. It's often called galactic archaeology. My involvement was more on the observational aspects of that, how we collect data on very large numbers of stars that led us to kind of population census type activities. So my trade, in a sense, was what's called survey astronomy, surveying large numbers of objects, whether they're stars or galaxies, and I did both, but so that people can then specialize, study those individual objects with a bigger telescope, for example, and look at the details of them. So survey astronomy also, so it lets you identify really interesting and unusual objects, but it also gives you these population census statistics. That extends not just to our own galaxy, but also to other galaxies in our neighborhood. Some specialize just in the local group of galaxies. That's how Milky Way, Andromeda, the Magellanic Clouds, the Triangulum Galaxy, and a few others. So there's these different specialities, even in what might be called extragalactic astronomy, astronomy beyond our galaxy, and that extends to the study of galaxies in other environments, in clusters, and eventually, you're looking at the big picture stuff. You're doing the science of cosmology, which is all about the origin and evolution of the universe. And I might mention just one more. Well, maybe not one more. There's several. Here's a branch that you might not have heard of, astro-seismology. It's about the vibrations of stars. There's a very strong field of a very strong field of practitioners in astro-seismology here in Sydney, at Sydney University. Another one is astrobiology, mixing biology and things like atmospheric science and all the things that we know about living organisms, putting them in a context beyond Earth, the origin of life elsewhere, all of that stuff. Astrochemistry feeds into that. That's sort of a fairly complete list of all the different disciplines within astronomy. But you see that there are many, many specialities, and some people never stray outside one of those specialist areas.
Is it possible that because of various specialties that sometimes they might be working on something similar, one makes a discovery that the other one should know about, but they'll never ever cross paths? Could that happen?
It's happens less now. I mean, that's why you publish your results, so that the learned journals, and there are many of those, some of which specialize in particular topics, but in those journals, it means that people with the similar interests will read them and see what your research is all about. So when I was a young astronomer back in the 70s and 80s, we kind of lived by the journals. Every month or whenever these things came out, you'd scan through to see what papers were there that were related to research that you were doing. Often you'd know people who were working in the same field as you, and you'd send them what was called a preprint. These days, that's all online. There's a thing called archive.
Back in the day, it would have all been actual physical paper.
Yeah, it was physical paper. It was a preprint of what your paper was going to say, so that you knew that in advance of it being published. So that side of it's different. But of course, with the way communications have changed, even things like social media are now used by astronomers to compare notes, to talk to one another, and so. It is much less partitioned than it used to be. People are a lot more fluid in what they know about the universe, which is often very important. So some people working in one field might have, for example, people working in galactic science, origin and evolution of our galaxy want to know about stellar evolution, the way stars evolve, and maybe about planetary physics and things of that sort.
All right. Thank you, Rennie. Lovely to hear from you, even if it was in writing. He usually sends us audio questions. Our next question comes from Mark.
Hello, Fred and Dr. Andrew. Mark here from somewhat sunny San Jose, California. Medium-time listener, first-time asker. The cosmic microwave background is the flash of light from when the early universe went transparent because formerly free electrons were finally able to combine with formerly free protons. My question is this. Why were there roughly the same number of free electrons and protons? If there weren't, we would be awash in a sea of remaining unmatched electrons or protons, but I've never heard any mention of this. So the numbers must have been relatively equal. How or why? Love your show. Keep it up. Thanks.
Good one.
Do you know the way to San Jose?
I'm thinking.
Yeah. Exactly. Sorry, Mark. You probably get that every time you tell people where you're from.
Yeah.
A certain generation. That's a really good question. And so the protons and electrons themselves were formed in the Big Bang. And so the products, basically the process that took pure energy from the Big Bang and turned it into particles, obviously essentially has parameters that will dictate how many of each particle are formed. And it's a really interesting question. And I mean, the match will not be perfect. And in fact, we know that about half of the matter that we expect, is it half? I think it's about half of the matter we expect from the Big Bang has not been detected until recently, when fast radio bursts show us that there is a soup of electrons actually existing between the galaxies. So there you have some evidence that there is an imbalance, because we've got a surfeit of electrons actually lurking between galaxies. That's what gives us the dispersion effect in the signal of the fast radio burst. So the match is not perfect. It may not even be nearly perfect, if we're talking about a factor of 2. So you've got lots of electrons left over, which is possibly what's happened. Then you're going to get you're going to get the atoms being formed and the universe becoming transparent, but you'll still have a surfeit of electrons, which I think is the situation we have. So great question though. Thank you for asking it.
Thank you, Mark. Always good to hear from you. Oh, well, no, I think he's a first-time questioner. So thanks for biting the bullet and getting involved. This is Space Nuts, Andrew Dunkley with Professor Fred Watson.
This episode is brought to you by Dragon Ball Legends, the ultimate Dragon Ball experience on your mobile device. Dragon Ball Legends features action-packed anime action RPG gameplay with Goku, Vegeta, Trunks, and all your favorite Dragon Ball characters. Summon your favorite characters from popular Dragon Ball anime series, such as Dragon Ball Z and Dragon Ball GT to Dragon Ball Super. Fight in real time against friendly or rival Dragon Ball players from across the globe in live PvP battles. Enter ratings matches with your favorite Dragon Ball characters and earn rating points and rewards. Unite with friends to defeat powerful foes in co-op. Dragon Ball Legends features the best anime fighting scenes on your mobile device. And now, Legends Festival is on, so you can get up to 300 free summon tickets. Are you ready? Download Dragon Ball Legends today. Available for free on both iOS and Android devices.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Well, we might as well get stuck straight into the next one, Fred. This comes from Mike. I like this question.
Hi, Professor Watson and Andrew. I'm a new listener to your podcast. I'm Mike from Manchester in England. I think it's a brilliant podcast. I love listening to all your theories about space and the questions you get in. I do have a question. It's about a recent discovery by the Imperial College London, Professor Riccardo Sapienza, I think you say his name, has discovered that they have done a double slit experiment, not in the traditional way, but using time instead of particles and waves using light. And they have found that depending on your reference point and your viewpoint on this experiment, you can actually see time in the future or in the past. Now, I'm wondering if this affects the way that we have been looking at the universe and using obviously the time, the frequency shift from the red spectrum to see the distance of stars and how old they are. Because this experiment actually changes the frequency of the light, it shifts it. So I'm wondering if gravitational lensing has, in effect, created this event of what they have found at Imperial College London, and we have actually been looking at the universe and recording it incorrectly in some cases, as the light that we're recording has actually got to us quicker than we originally thought, or actually slower than we originally thought, meaning that we possibly have got the age of the universe all wrong. I'd love to hear an answer to the question. I think it's quite interesting. So great to hear back. Thank you.
Thank you, Mike. Wow, that's pretty deep. We have had the question come up officially, scientifically, that some believe that the age of the universe is off. So what he's asking is, through this double slit experiment using light, are we in fact seeing, I'll use the terminology, a time slip, which could be forwards or backwards? Interesting.
Yes, I'm actually just looking at the. I hadn't heard of this work, Mike. So thank you for alerting us to it. I'm looking at the Imperial College press release, which was published back in April this year. Imperial physicists have recreated the famous double slit experiment, which showed that light behaving as particles and a wave, but in time rather than in space. And so what they're doing is looking at materials that can change their properties, optical properties, very, very rapidly at sort of femtosecond timescales. I can't remember what a femtosecond is. It's very small. And then I'd need to really read the article to be across exactly what's happening. But it clearly, yes, so there is, exactly as Mike said, a change in frequency involved. So some colours are cancelled out in white light, and some are enhanced. I really need to sit down and read this article to understand exactly what's being talked about here, because I can't really comment on the effect it has on our understanding of light coming from distant objects. My guess is we're talking about such an extraordinary circumstance of this optical property changing over time, that you're talking about very, very special circumstances that really have no impact on our understanding of, what you might call cosmological redshift, which is the redshifting of light. But look, I'm going to read it. So maybe we can put that on the list to come back to, Andrew, because it is a very interesting piece.
On the homework list.
Very interesting piece of work. One of the co-authors of the paper is a very well-known name, Professor Sir John Pendry, a very well-known physicist. His comment is the double time slit experiment opens the door to a whole new spectroscopy capable of resolving the temporal structure of a light pulse on the scale of one period of the radiation. So it's really about how light changes in nature. in general. But yeah, let me come back to this because I think it's worth pursuing. It's a really interesting piece of work.
Okay, will do. Thanks, Mike. We'll get back to you shortly. Next question comes from Justin, who says, "Hi, Fred and Andrew. I wanted to ask a question about the recent LF bot, luminous fast blue optical transient reports. It seems this is being reported as a brighter and more energetic explosion than a supernova. But I have to wonder
I believe
if
that's
this
right. Yes. So
a misreporting of an event that is highly coordinated rather than
nobody really knows what they're. No, nobody knows what they are.
Yeah. Well, that's some sources are reporting LF bots as a flash that repeats on regular or irregular intervals, and that just reinforces my opinion that it may be naturally occurring laser, much like the masers we already that know already occur. What are Fred's thoughts? Thank you, Justin.
Yeah, really interesting. Masers are microwave lasers, effectively, and they are well known in space. They're in the radio regime. They're well studied. I don't believe that there is an optical equivalent in acting in nature, because it's not something that I've ever come across. So I think these transients are. It's an interesting thought, though. The possibility of there being optical lasers that occur in space. If you look on Wikipedia, as you always should do, and don't forget to contribute to Wikipedia either, because it needs money. The precise definition of what constitutes a fast blue optical transient is currently contentious in the literature, rather largely defined by the observational properties rather than the underlying mechanisms or objects. And, the comment here, even within the class, growing samples are beginning to reveal significant variation in properties when the objects are studied in greater detail, potentially indicative of different progenitor channels or explosion mechanisms. In other words, nobody really knows what they are. The idea of them being optical lasers is an interesting one. I suspect one of the things that puts against that is that I think these things are broadband. I think there's, they're not a single wavelength that is being emitted, whereas generally in anything that's stimulating emission, which is what the laser process involves, you essentially get monochromatic light. It's very interesting. A number of when you look down a list of fast blue optical transients, there's a whole mixture of them. They date back to 2018. Various observatories have observed them, and I think one has been one of the recent ones is the biggest. That's the object known as the cow. I'm not quite sure why it's known as a cow, but it is, and it's probably relatively nearby, but its peak luminosity exceeds that of the luminous supernovae. So we're talking about really mysterious objects here, about which, certainly my knowledge is relatively limited. It could be possibly black hole related, something a bit like a quasar, but emitting basically short period, i.e. transient amounts of emission, with perhaps radio emission as well as the visible light and X-ray emission, but coming from different parts of whatever it is we're talking about. Some dense, perhaps almost a black hole inside a dense medium that's having all kinds of basically pulsations. They may be relatives of gamma ray bursts, which are gamma rays that are focused in a particular direction.
All right. The mystery continues, Justin, but there's all sorts of ideas, but no one really knows. Thanks for your question. Next one comes from Nigel. This one should be quick and easy, Fred.
Hello, space nuts around the world. Hi, Fred and Andrew. This is Nigel from Brisbane, Australia. I have a question about launching satellites into space. More exactly, I have a question about launching privately owned non-government satellites into space. In recent years, there's companies like SpaceX and Rocket Lab in New Zealand who launch privately owned satellites into space. But before they were around, I wanted to know who was doing it. We've been launching privately owned satellites into space for over 40, 50 plus years now. So can you tell me who was launching them into space? Was it all NASA or was it some other company? Terrific. Love the show. Keep up the good work. Bye.
Thanks, Nigel. Yeah, that's a good point. I think NASA was certainly doing it. I think Roscosmos was getting involved because they needed money. I think ESA was doing it for a while there, and they might still be.
Well, most private satellites, certainly over the last 40 years, have been communication satellites. So we're talking about things like geostationary satellites, which are in those orbits that make them very suitable for communications. They are, I think, almost exclusively privately owned by companies like, Telstra here in Australia, other communications companies. That's the main one. Then, as time's gone on, you've got universities which launch effectively private satellites for research purposes. Somebody pays the bill on these, so they're not always being paid for by NASA or ESA or Roscosmos or JAXA, the other major space agencies. But I think your comment really is about the launch vehicles, perhaps, Andrew, that their launch vehicles themselves were often funded by these space agencies. But even there, launch agencies now are private concerns. ULA is one, the United Launch Agency. SpaceX is another. Blue Origin is another. So it is, the space is privatized in a very, very big way. And in some senses, the government agencies are now the smaller players, except for the defense agencies, which of course are major players about which we know virtually nothing.
Yes, exactly. Exactly, with their mysterious shuttle that's up there for years at a time, all that kind of things. But I suppose it's an expanding and developing market, isn't it? I think even Australia is looking at private satellite launching in the not too distant future. So it's But I suppose the government agencies before privatization came along were probably the ones, but it's a ever changing market would be probably the answer, Nick. But thanks for your question. We're going to take a breath and then we'll try and whip in a few more questions before Fred has to go. He's on a very tight timeline today.
Experiences are what people love the most about travel. That's why they love Viator. They have over 300,000 bookable experiences and something for everyone. Plus, their travel experiences have millions of real traveler reviews, so you have the information you need to book the best activities for your trip. Download the Viator app now and use code Viator10 for 10% off your first booking in the app. One app, over 300,000 travel experiences you'll remember. Do more with Viator.
When picking a commerce platform, you have two choices.
Oh, you piece of...
Or, yeah! That's the sound of selling on Shopify, the commerce platform that supercharges your selling online and in person. Why battle inferior platforms' weak tools? And limited integrations.
Would have helped to know this.
Join the millions of businesses growing on Shopify and ignite your selling.
Less, more.
Start your free trial today at shopify.com/profits23. Shopify.com/profits23.
Space nuts.
Okay, Fred, we've got a question now from Rusty. I absolutely love this one.
G'day, Fred and Andrew. It's Rusty in Donnybrook. Thank you so much for answering my question about the, from one point of view, trillions of years old infant universe that we're living in now. The pinhead size for all those trillions of years and then suddenly bursting into life. So there's got to be more, doesn't there? So what's the possibility of one or more of these things existing embedded in our own universe? They'd only be detectable by their gravity, of course. So the one that comes to mind for a relatively close example is the Great Attractor. But there could be more of these things further out. So, what's the possibility of that? Cheers, guys.
Thanks, Rusty. I've never thought about this as a possibility, Fred.
So conventional wisdom doesn't allow that to happen because
Rusty's not conventional.
No, he's not. You can't have something that's trillions of years old in something that in which billions only existed for 13.8 billions. Yeah, he did mention trillions of years. Yeah, so. But the Great Attractor is pretty well understood now, and because with infrared telescopes we can actually see some of the galaxies that are causing that attraction. Remember, the Great Attractor is a region of space which kind of lines up with the Milky Way, which is why we can't see it with normal optical telescopes. But it's where lots of galaxies seem to be heading. Hence the name, the Great Attractor. My guess is
it a John Deere or a Massey Ferguson? The Great Attractor.
Yes, I'm with you there. Yeah.
I think
international harvester to be precise. Yeah. Anyway, So I think that's a nice thought, but I'm not going to buy that one. I don't think. Thank you, Rusty.
Nice try, Rusty. All right. We've got a question from Nick. The Psyche mission is testing the deep space optical communication system. Kindly explain what that is and how it works. Thanks. Love the show in spite of the bad dad jokes. Nick. Oh, dear.
Indeed, it is. It is actually a test bed for optical communications, and in fact, they're if you go to their webpage, which I've just done, the Psyche mission, Jet Propulsion Laboratory webpage, Psyche is going to an asteroid called Psyche, which I studied actually when I was doing my master's degree.
Yeah.
Asteroid number 16, Psyche. It's got an interesting orbit. But just reading directly from the Psyche website, we have one of the sections is deep space optical communication, and it says the Psyche mission will test a sophisticated new laser communication technology that encodes data in photons at near infrared wavelengths rather than radio waves to communicate between a probe in deep space and Earth. Using light instead of radio allows the spacecraft to communicate more data in a given amount of time. And the DSOC team, Deep Space Optical Communication team, is based at the Jet Propulsion Laboratory. So they've got receivers there that are picking up infrared radiation coming from the Psyche spacecraft, and with much higher bandwidth than what we would have for radio waves.
Fascinating. I think I read the other day that there was some kind of signal that came back to Earth and they don't know where it came from. And I think it was described as a laser. I don't know if that's what it was, but they don't know its origin. And it seemed to come from the portion of the universe that's, got nothing in it. So whether or not it's been moved by something else and intercepted by Earth, I don't know. But it was that's another mystery we have not solved, Fred.
And I need to check that one out as well to find out what it is that's of interest.
Yeah, I should have sent it to you. I usually do when I see something like that. Can we squeeze in one more?
I'm already in the other meeting, Andrew.
Oh, okay.
With my camera turned on, I'm just about to turn it off. So they're not seeing me. Yeah, look, we've got a minute or two because I can see on the screen that
they're making coffee.
Happening. So let's keep going. Yeah.
Okay, this last question comes from Robert.
Hi, I'm Noah from Mackay. I just have a question about whether there is any stars in the night sky today that weren't there 50, 60 or 100 years ago. Is there any stars in the sky that the light has finally reached Earth and we can see them now and we couldn't so long ago? But yeah, I absolutely love the podcast. I listen to every episode, so keep doing what you're doing because I'm loving it. Cheers. Hope you have a good day.
Thanks, Noah. I think I called you Robert. My apologies. But hello to Mackay. I used to live there many, many years ago. Yeah, that's a good one. Only new stars in the last couple of 100 years. I suppose this is something that would be obvious to some, but down here in ordinary world, we don't really think about that.
You probably over timescales of tens of thousands of years, you'd see the evidence of new stars, probably maybe hundreds of thousands of years, because star formation is a process that takes a little while, and they don't just pop into existence all of a sudden. Some stars do brighten, so Noah's right in the sense that, for example, the First Nations people in Australia, we think some of them, and elsewhere, we think some of them have seen stars that for a long time were below the limit of naked eye visibility, but then that brightened up to the extent that they actually became visible. And in fact, some stars we think have brightened up to become very bright indeed and then faded away again. So that's an intrinsic property of a star that's whose environment is changing. Often it can be something that's blanketed by dust. That's one of the ones I'm thinking of. That's right. So the stars come and go in that regard. But if you had a telescope, you'd still be able to see it. Even when it was at its faintest time. But nothing that's just kind of switched on out of the blue like that.
So for several generations, the sky probably hasn't changed much.
That's exactly right.
Yeah. All right.
Yeah. And the other one is if you get a nova, which is a star that has a bright outburst, it may have been below visibility beforehand and suddenly gets bright. And of course, supernovae do that as well. You have a very dim star that suddenly becomes extremely bright. So all of those are events that are related to this. And I see, Andrew, my meeting has now started.
All right.
I'm going to have to go and join it.
Cut it very fine this week. Thank you.
So I'll let you do the wind-up.
Thank you, Fred, and we'll let you get to your meeting. It's been great as always. Fred Watson, astronomer at large. And don't forget, if you have questions for us, send them in via our website. We'd love to hear from you, whether they're text or audio questions. Have a look around while you're there. Christmas is coming up, so don't forget to visit the shop. And if you're interested in becoming a patron, just go to spacenutspodcast.com or spacenuts.io. That's just about it. Thanks again to Fred. Thanks to everyone who contributed to the 380th episode of Space Nuts. And thanks to Hugh in the studio for pushing all the buttons and ringing all the bells and for pinching Fred's dog's bottom so that it made a lot of noise during the show this week. And from me, Andrew Dunkley, thanks for your company. Look forward to seeing you next time on Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.
Does this make any sense? And of course, if you had something like a quark star, which is being theoretically considered singularity.
I'm going to have to stop, Andrew, because I've got to go and attend to that. Hang on a sec. Hello. Fine, thank you.
Thank you.
That was the doorbell. So cool. Straight face.
Sorry about
that. Love your doorbell.
Yeah. I knew as soon as he started what had happened.
Someone was there.
Yeah, it's actually the cleaner.